Hello. So I'm back here. We will talk about exercise 4. Exercise 4 is about sampling distribution. The key here is that the statistics that you got from the sample, it is a random variable. It is not a constant that never change. So you have to distinguish between two keywords, a parameter is a measure that describes the characteristic of your population. For example, if you want to calculate what is the average age of UTM undergrad student, then the average age of all UTM undergrad students is a parameter because it is the measure of the population you are interested in. However, if you only sample, let's say 30 students and you ask for their age and you calculate the mean of their age, then that number, it varies across different sample, right? Then that one, you call it a statistics. This one is a measure computed from the sample. Okay. Just imagine like this, your whole population. And like you have the average age of all UTM undergrads. This one is a parameter because it captures the whole population that you are interested in. However, if you only sample 30 students from UTM undergrad and you calculate their average age, UTM undergrads, then this average age is a statistics because it is computed from a sample. And you might notice that if you choose different sample, but still in our population, this different sample might give you different average age. Okay, these two values might be different. And let's say you repeat this experiment many times, and each time you calculate the average age of group of 30 UTM undergrads. So you will have like different average age, like from group 1, from group 2, from group 3, ... to group N. And then you graph it. You graph the distribution of these sample mean in, let's say, histogram, where the x-axis might represent average age of group of 30 UTM undergrads. And this one will show the frequency. Like how often do you get that average? For example, from group 1, you calculate the average, it is 18.5. From group 2, you calculate the average age is 19. Group 3, you calculate that the average age is 18.5. Then here, 18.5 would show up 2 times and 19 show up 1 time, something like that. So in conclusion, the statistics that you calculated from a sample, it is a random variable. it change corresponding with your simple. And there is a very, very important theorem that you will need to use. It's called central limit theorem. What it says that no matter what is the distribution for your population, whether it is normal or is not normal, then the simple mean denoted by x bar is still have a normal distribution where mean is the same as the population mean. The standard deviation is population standard deviation divided by square root of n. This one is also mentioned in your lecture. If you don't remember, you should check it back because this one is very important. Okay. So now we will actually try to solve exercise 4. And one condition to apply this central limit theorem is that the sample size have to be at least 30 if the population distribution is not normal. Otherwise, if your population is normally distributed, this always applies as well. No matter that you have a small sample size or large sample size, if your population is already normally distributed, then the sample mean is also normally distributed regardless of your sample size. However, if your population is not normally distributed, then you need a sample size of at least 30 so that the central limit theorem applies. Here we have number of accidents per week has this mean and this standard deviation. So we let X represent for number of accidents per week. Then X, I plan to write X follow a normal distribution, but it is not given here. Look at this, they don't give us what is the distribution for the population. They just tell us that it has this mean and this standard deviation. So we will write, we know that the mean is 2.2 and the standard deviation is 1.4. For question 1, we let X bar represent the mean of number of accidents per week during a year. So here, X represent number of accidents per week. X bar represent the average number of accidents per week across 52 weeks, which means that we look at what is the number of accidents in week 1, what is the accidents of what is the number of accidents in week 2, ... what is the number of accidents in week 52. We add them up and then we divide it by 52. That's how we get the average number of accidents during a year, which means that here our N is equal to 52, right? Because we record number of accidents per week for 52 weeks. So the number of observation, the number of weeks that we observe is 52, which means that we don't need to know that the population is normally distributed or not. It might not. However, when we have N is equal to 52, which is greater than 30, then central limit theorem comes in, and it tells us that X bar will follow a normal distribution. The mean stay the same, 2.2, but the standard deviation is this standard deviation, 1.4, divided by square root of N. N is the number of observation, which is square root of 52. If you are confused, you should stop and maybe look back at the lecture slide or the textbook to make sure that you grasp the concept well before we proceed any further. So that is the question for part 1. Question for part 2, we want to find the probability that X bar is less than 2. Here we see X bar is normally distributed. So what does it remind us of? It reminds us of Z, a standard normal random variable. So in order to calculate this probability, I will standardizing X. Recall that to get Z, we take any normally distributed random variable minus its mean and divided by its standard deviation. So here, our X is X bar. X bar is a normal random variable that we are considered here, minus the mean of X bar is a mean of X bar. And this is a standard deviation of X bar. Do not divide it by this standard deviation because it is not the standard deviation of X bar. This one is a standard deviation of X. So this one, I have to take X bar minus mean divided by standard deviation less than 2 minus mean of X bar, which is 2.2. And divided by standard deviation of X bar, which is 1.4 divided by square root of 52. The first term here, it is Z. The second term here, if you calculate correctly, you should get minus 1.03, like this. So if you look at the graph, 0 is here. So minus 1.03 is somewhere here. I want to find this area, right? However, our Z table only provides this part. So we have to somehow use the information of this to get to this. And we realize that normal distribution is symmetric. So if I have, here I have negative of 1.03. Here I have 1.03. And this area is the same with this one. These two areas are the same. And this one is just this part, 0.5 minus this area, right? So here, I know that probability of Z less than minus 1.03 equal to probability that Z is more than 1.03, which is this one. And it is equal to 0.5 minus probability that Z fall between 0 and 1.03. This term is when we should use Z table. We want to find the area between 0 and 1.03. So if I look at 1.00, 1.01, 1.02, 1.03. This thing here. So I have 0.3485. And it is 0.1515. And it is our final answer for part 2. For part 3, they ask what is the approximate probability there are fewer than 100 accidents at the intersection in a year. Which means that if you record the number of accidents in week 1, number of accidents in week 2, add up to number of accidents in week 52, then what is the chance that that sum is less than 100? There's actually a formula for this. We do have general formula, but I didn't see it in your lecture. So we will convert this one to the simple mean for now. So if you add up number of accidents in week 1 plus number of accidents in week 2 up until number of accidents in week 52. What is the chance that this sum is less than 100? What is this chance? So we can represent this one by by the random variable. Number of accidents in week 1 is just number of accidents per week, right? It represented by random variable x. Number of accidents in week 2. Let's say this one is x1. This one is x2. And number of accidents in week 52. Okay. What is the chance that you add them up and it is smaller than 100? So here, if you take the sum and divide it by number of observation, I divided by 52 from both sides. This one will become x bar, right? If you take the total and you divide it by number of observation, then you have the mean. And what is the chance that x bar is less than 100 divided by 52? Does this look familiar to you? We just did it. We just did something similar here, right? These are the same problem, it's just different number. So now recall that x bar follow a normal distribution. Mean is 2.2 and standard deviation is 1.4 divided by square root of 52. So this one, I can standardizing x bar minus the mean of x bar divided by standard deviation of x bar less than 100 divided by 52 minus mean of x bar is 2.2 and divided by standard deviation of x bar is 1.4 divided by square root of 52. This part is just z. This part, if you calculate correctly, you should get like minus 1.43. If you believe that I made a miscalculation anywhere, feel free to post on Piazza and I will change the solution accordingly. So here, if we look at the graph, we have 0 and we have minus 1.43. We want to find this part, right? So again, it's the same as probability that z is greater than 1.43. So I draw something symmetric here. So these two areas are the same. And in order to calculate this, I can take 0.5 minus probability that z is between 0 and 1.43, like this. The second term I can look up in the z table, 1.43, 1.400, 1.401, 1.42, 1.43. This is here. Sorry, I think I mispronounced it. This one is 1.40. This one is 1.41, 1.42, 1.43. So we have 0.4236. And then we calculate, we just get 0.0764. And this is our final answer for part C. If you have any question, feel free to post on Piazza.